Section 15.6.3 Laddering. When the integers are very large, this is still a bit slow because we are multiplying and dividing large numbers. The laddering technique can be used to avoid this. It uses two congruences for each step. Instead of multiplying the coefficient of x by ever-increasing numbers to make the value close to the modulus, the laddering technique is to multiply the coefficient in each congruence by a small number to make it close in value to the preceding coefficient. This requires an extra congruence to get the process started. For this purpose, we use the congruence mx is congruent to m, mod m, which is equivalent to 0x is congruent to 0, mod m. Let's look at an example using larger numbers. Since 28338689 over 6114257 is about 4.635, multiply by 5 and subtract to get. Here 6114257 over 2232596 is about 2.739, so multiply by 3 and subtract to get. Continue this way to get successively. Each of these examples used a prime modulus. The situation gets more complicated when the modulus is composite. I will not cover all of these complexities here. The case that is of most importance for cryptography is when the modulus is a power of 2, such as 2 to the power of 32, or 2 to the power of 128. In this case, the multiplier that you choose at each stage must be odd. So, instead of rounding the multiplier to the nearest integer, you always round toward the odd integer. For example, 3.14 would be rounded to 3, and 3.99 would also be rounded to 3. Res-MH using laddering can be called Res-MHL. Section 15.6.4 Continued fractions. Once you have two or more linear congruences, you can reduce the coefficient of x far more quickly by using a technique called continued fractions. A continued fraction is a way of closely approximating a decimal number by a fraction. Consider the decimal number r equals 0.13579. r is somewhere between 1/7 and 1/8. More precisely, r is about 1 over 7.3643. This can also be written as 1 over 7 plus 0.3643. Notice that the plus sign plus is in the denominator of the fraction. This indicates that the addition is done in the denominator as opposed to adding the two fractions 1/7 plus 0.3643. The fraction 0.3643 can be approximated as 1 over 2.745 or 1 over 2 plus 0.745. So r is now 1 over 7 plus 1 over 2 plus 0.745. Here 0.745 is very close to 3/4, so the approximation can be 1 over 7 plus 1 over 2 plus 3 over 4. To get that back to an ordinary fraction, just work backward. The fraction 11 over 81 is 0.13580, which differs from 0.13579 by only 0.00001. As you can see, this method gives excellent approximations. Let's try that example from section 15.4.3 again. For the second congruence, we use the 0 equals 0 trick. Here, 6114257 over 283388689 is. A good rule of thumb to get a close approximation is to stop just before a large denominator, in this case 24. Truncating the continued fraction before 24 gives, which works out to 241 over 1117. Multiplying the 6114257 congruence by 1117 and the 283-38689 congruence by 241 and subtracting gives. This reduces the coefficient of x from 6114257 to 1020, a factor of 5994. So the continued fraction method uses far fewer steps than other methods. However, it is tricky to use because the coefficient from one step may be much larger than the next coefficient. For example, 6829625069 versus 1020. You can balance the coefficients by alternating between continued fraction steps and half steps.